So the next thing that we're just kind of introducing here, just getting started into it, is going to be Boolean algebra. Something a little different than what you've seen in algebra before. So when we were talking about math, I believe it was last week's lectures. It was in a very early chapter. It was like in chapter 1, but we didn't need it till week 3. So it was in the reading way before the lectures. But when we were talking about that, we discussed the arithmetic operations. That doesn't look like an E. The operations that we can perform on our numbers to get results, right? Like add, subtract, multiply, divide, modulus, and exponent are the main ones that we're going to be working with. And we can use like addition to combine two numbers, all right? It's an operation, a combinatorial operation. Or subtraction, we can subtract two numbers, which is a reduction type of operation we can perform on these two numbers. And kind of all those things we can do with numbers. So that's what we're going to look at for Boolean algebra, for an introduction to Boolean algebra, is our operators for this other type of math we can do. And the term we're going to use is logical operators. And we just saw all the words we're talking about set theory a moment ago. So our logical operators are going to be like and, which is an inclusive, just like we use it, right? If you need a full consensus, right? You have a room, 3 people, and you're going to take a vote and ask people, and 1 says yes and 2 says no. Well, there's no consensus, right? 2 people saying no, that's inclusive, but that yes prevents there from being a consensus all the way across that vote. So an inclusive operator. We also have the or, which is kind of like we would use the words. Somebody asked about going to dinner, tacos or hamburgers. And or, it's like, okay, I'm hungry. Either one sounds good. They both sound like food, so or would be good in that situation. But tacos and hamburgers probably have to go to 2 different restaurants to get that. Because Taco Bell sells tacos, but not hamburgers. McDonald's sells hamburgers, but not tacos. Sometimes, I guess they have their apps. Those are like tacos. But, with an and, you need that inclusiveness. You need to find a restaurant that sells both hamburgers and tacos. But or, either restaurant's fine. As long as they sell food, right? As long as the answer is there somewhere, sort of thing. It's not as inclusive as that. And we also have not. That it isn't something, the negation of it. So we have a couple symbols we're going to use for these. And I guess I'll start with the logical case. Now there's one more I'm going to list out here because it's in the list of things to learn. I'm not really sure where to put it, but we'll get back to that in a moment. But we have some symbols for these. And we typically use an ampersand when we're coding that. So we have either 1 ampersand or 2 ampersands. And the difference is 1 ampersand is what's typically refers to bitwise AND. So if we had 2 bytes of data and we wanted to do an AND, well, I'll just do 4 bits because that's a little 1. So if we were to do a bitwise AND, it's going to check each bit in particular. So it would get a result from this bit. 1 and 1, well, it's inclusive. Both of them have a 1. 0 and 1, they're not both the same thing. They're not both 1s. So it would result in a null. We'll talk about the results here in a moment, but here again, we get some sort of result. But we check bit by bit with 1 ampersand and get the number of bits we put in. If we use 2 ampersands, that's just what we would think of as a regular AND. Those are different numbers, so they're not inclusive to each other. So this is the one we typically use. This is included in every programming language, so I want to mention it here. And working directly with machines at the electrical engineering sort of level, I use this all the time. But as far as programming and years and years and years of writing code in high-level language, I've never come up with a reason to use the bitwise AND encoding. But it's included in every language, so there must be a reason. It's just not in any of the things I've done. Whereas working directly with the machine in machine language, it shows up all the time. So that's our typical symbols for that. An OR is the pipe symbol. You may not have known the name of it, the vertical bar. It's right above the enter key. All the way right above the enter key, above the backslash. So shift and backslash key, that vertical bar. And just like this, one pipe symbol is going to be a bitwise OR. So the same thing, it goes bit by bit, and our result will be the number of bits we put in. But most often we use 2 pipe symbols for just a regular OR, and then we'll compare to like 8-bit numbers, and our result will be a 1 bit. Just a yes or a no, a true or a false. So that's the logical part. Our yes-no things, our true-false. We feed in 2 things, and the same way we would feed in 2 numbers and combine them with addition, we feed in 2 numbers and combine them with and or, and our result is going to be a true or a false. So that's the Boolean part, the binary algebra. It's binary algebra. Well, Boolean is somebody's name, bool. But it's the binary state algebra, yes or no answers. And our symbol for not, the abbreviated one, is usually going to be the exclamation point. Exclamation mark. I've heard people just call that a bang before. I don't ever refer to it that way. I always just say exclamation point, or sometimes when I'm reading code, I will just read that as not. But I have heard people call that symbol bang. I have no idea what the origin of it is. Probably go back to elementary school. That's a good way to explain what that symbol does in English. And maybe it's just fun to say bang when you're reading code or something. But I usually, when I see that, I just go ahead and read it as not. So typically we'll type those symbols because they're easier to type than write out the words. But in most languages, we can use either one. We can use both of them interchangeably. Okay, I washed off whatever was on the board there. It wasn't chalk, but that is the word not. Wash that off between scenes. So some other symbols we can use for these. So these are the typing versions. I guess I could put a box around this and write type. Typing. We can use those. We think this, we're going to think and or not, because most of us think in words. But we can type the word and, or we can type 2 ampersands. And it behaves exactly the same in most programming languages. Some other symbols that we can use, and on my way through school, the only place I saw these was working on the engineering tech degree in electrical engineering classes. But it's on the list of things to include here, so I wanted to make sure and go ahead and include it. And a couple years ago, I was teaching this class, and 2 people were taking CSCI 101, Computer Science 101, online at the same time, and they said they saw these online as well. and the Computer Science 101 class as well. But we have some other symbols which I'm familiar with them from electrical schematics that we would use for and in an electrical schematic. So I saw it in electrical engineering classes, but it's included here. So we'll go ahead and write these symbols. So our symbol for and kind of looks like this. So on a schematic, you'll see this little half egg thing. So we have two lines coming in, and then kind of half an egg and one line coming out. So whatever signal is feeding in, a 1 or a 0 coming into each line, and then we combine them with an and get the output from that. So the actual the diagram for the physical representation of and in a circuit. And an OR gate, I always have a little bit of trouble drawing these. Well, not a little bit of trouble. I just have to draw them really, really slow for some reason. I found if I draw them fast, they do not come out very well, but kind of like that. Yeah, I don't know how to describe the shape. Just like dented in, kind of curved in. So that's the symbol for OR on an electrical schematic. The physical component of an OR gate. And then NOT looks like we draw a triangle, but what it really is this little dot here. This little dot at the end represents OR. Oh, kind of a defective piece of chalk. Because we can combine these. So like, NOT and, we can combine multiple logical operators just like we can combine addition and division, right? We can add some numbers and then divide by another number. We can combine our operators, so like NOT and, we would usually say NAND. And the symbol for that, as far as the electronic schematic component, an AND gate is the combination of them. So symbol for and then the symbol for NOT. So a little dot afterwards. Or you might see it with the little dot first. Both of those would be NAND, which is not AND. And a similar thing for NOR. We can put the dot on either side. But we can combine those operations, NOT and OR. So those symbols you want to include. There's some other ones we're only going to talk about briefly. Since I have NAND here, I'll talk about XOR as far as gate. That's exclusive OR. It'll make more sense when we go talk about the results of an OR. But exclusively one or the other, but not both. So exclusive AND's inclusive, and XOR is exclusive. So one or the other, but not both of them. And our symbol for that, as far as these go, is like an OR gate, but there's an extra line back here. Yeah, and if you're watching the supplemental videos that I made to address questions I've heard before, since we're not in the classroom, where people can ask us, "I've drawn these symbols," or a couple weeks ago we were doing the math, and I said there's one about doing machines in math. So now that you've seen an XOR and an AND gate, that's the symbols used in the supplemental video showing how a machine actually does math. So we're up to that point now. I think I mentioned delaying that supplemental video until we've seen that, but that's the two symbols we would need for that. And we're going to talk about the results of them here in just a moment, so we'll keep that around. I'm going to have to erase this to start talking about results. So one other thing that kind of fits as an operation, or well, two other things. There's a precedence, there's an order we have to follow. They have different precedents. So in our regular operations, like we're used to with numbers, we do exponents way before we add, right? You probably heard PEMDAS or some in math class, please excuse my dear Aunt Sally. a nice polite way to say it. The inappropriate or funny ones are better to remember, but obviously can't be stated in a classroom. But something that PEMDAS, the order we follow, parentheses, exponents, multiply and divide, going from left to right, because sometimes the order doesn't matter and sometimes it does. So we just always go left to right. That way we don't have to worry about whether the order matters. And then add and subtract going left to right. We have the same thing going on here. And, well, the reason we do exponents way before we do addition is because exponents are unitary operations. They only take one number. It looks like we have two when we do something, but in order to square a number, the only thing we need to know is which number is being squared. So that operation only takes one number. So we do the operations, the unitary operations, before we do the binary operations. Because like addition takes two numbers. 1 plus doesn't mean anything. We need to know what number we're adding 1 to. So we do the unitary ones first. And kind of the same thing here. Not is a unitary operation. We're going to negate the thing right after the not. Whereas and or are both binary operations. So we need to do our unitary operations before we do our binary operations. And then likewise, if we have big long strings of these, we can wrap them in parentheses, so we want to do any grouping first. So we do any grouping, the parentheses first, then our unitary operations, and then our binary operations. So I like to state it that way because then it's the same as our arithmetic order of operations. We do the groupings, the parentheses, then our unitary operations, exponents, and then our multiply and divide and add and subtract all the binary operations. So it goes in that order. So kind of the same order, but there is a precedence to them. We'll do, the nots will get done before the ands get done. There's that. And one other thing, it's on the list to include, with our logical operators, in a classroom, if I wasn't abbreviating this, I would write out 17 things that show everything we can do in Boolean algebra. 15 of them should be quite obvious when we do our truth tables to show how the results come about. 15 truth tables show an example of all the combinations. Thorough examples of all the combinations. Like obviously there's more combinations, but it's enough to get everything across. But then there's 2 more, so there's 17 examples I would write out. And the other 2 are what's called De Morgan's laws. And I've seen it with and without the E here. There's always an apostrophe. But I tried to Google it and saw it both ways again. So De Morgan's laws, it's obviously originally in a different language because I've seen it written with and without the E on valid sources. So I'm going to write it this way. We'd say it the same way, De Morgan's. And this is a way of combining them. It's a set theory thing. So it applies to set theory in general, but it applies a whole lot in Boolean algebra when we're just doing all our set theory operations on yes-no questions. In particular, if we're negating things and combining them. So there's kind of 2 forms of them, and they're equality, so they'll go both ways. So I'll use these symbols. The exclamation point for not, ampersand, 2 ampersands for and 2 pipe symbols for or. So not A and not B. Well, that will give you the exact same thing as A not or B. So not A and not B is equivalent to A nor B. Nor being not or. Not or just becomes NOR, because that's a whole lot easier to say. That's actually an English word. NAND, we had to make up a new word, but that one really is an English word, and it kind of means the same thing. So not A and not B is the same as A nor B. And that goes the other way. If we have A nor B, we could rewrite that as not A and not B. And vice versa. It goes the other way too. So not A or not B will produce exactly the same result as A NAND B. So those are important ways to rewrite things because like sometimes these can get kind of complicated. So that's De Morgan's laws. Draw a box around there. And we'll put a box up here. These are our logic gate symbols. Which there is one of the supplemental videos is showing what these are. I just talked about a whole lot of complicated stuff, right? This is not hard. This is, you've probably heard computers are just combinations of switches. These are our combinations. So that's in a supplemental video. If you want to watch that, it's only like 20 minutes long, I think. But these are our switches. That's what logic gates are. So putting some labels on here. So here's our logic gate symbols, which I'm more familiar with from electrical engineering classes. De Morgan's laws are a big thing in set theory, and they show an incredibly large amount with Boolean algebra because it can simplify complicated looking statements very, very nicely. And then just our basic logical operators. This is how we combine these true, false, yes, no type things. So I'm going to erase the board and get ready to talk about those combinations, set up some truth tables, which is the way we notate the result in Boolean algebra. So I'll erase the board and get to that. Step out of the way so you can see all those labels for those taking notes and stuff. Okay, so the last little thing I want to write here is truth tables, which is how we list out our results in Boolean algebra. So let's start with a not. I'm going to do all our logic gates here. So a not is a unitary logical operation. A not gate means we'll have one input and one output. So we have some sort of input and some sort of output. And our input can either be on or off, be true or false, yes or no. And like we've seen before, we're going to represent that with the 0 and 1, because those are quick, easy symbols to write. And depending on the situation, we might use one of the other ways to phrase that, just to make more sense out of it. But not is the negation of it. So the output is whatever the input is not. So if we input a 0, the output of the not gate will be a 1. And vice versa, if we input a 1, the output is what's not 1, which is a 0. So just little tables to list out all our options. So an AND gate. So AND is a binary operation. So we'll have two inputs. I'll call them A and B, and then an output. And just to be systematic, to make sure you don't miss anything, because we're just going to do some simple ones here, but they can get fairly complicated. So a good systematic method is however many inputs you have, 2 to the number of inputs will tell you how many rows there are. So we have 2 inputs, so we're going to have 2 squared or 4 rows in this table. If we had 5 inputs, we'd have 2 to the 5th or 32 rows in the table. So a good systematic method, I'll leave that up there for a moment so it's in the way, A good systematic method is to start with the first column and do half of them, figure out how many rows you're going to have, do half of them as zeros, or F's if you would rather write P and F for true and false, or Y and N for yes or no, or spell the words out. Whichever works best with your mind. I'm just going to write the traditional ones and zeros, quick, easy symbols that we can tell at a glance. We can tell them apart at a glance. So do half of them as zeros and half of them as ones. Then cut that in half. So we did 2 and 2. So half of 2 is 1. So then we do 1 of each until we get it all filled out. So if there was, say, 8 rows, we'd cut it in half, do 4 of each, 4 zeros, 4 ones. And the next one, cut that in half. Do 2 zeros, 2 ones, 2 zeros, 2 ones. The next column, cut that in half. 0, 1, 0, 1, 0, 1, 0, 1. And that's just a quick systematic method, a good systematic method to make sure you don't miss anything. So figure out how many rows it is, cut it in half. The first column is half zeros, half ones. And however many that is, cut that in half for the next column and keep doing that until you get all the columns, all the input columns listed. So and is inclusive. So filling this out, words on and off make sense. Right? We have two switches, like 2 light switches on the wall. Right? They're and. So if both switches are off and off, the light's going to be off. If one switch is off and one switch is on, off and on, well, that's not inclusive because the off is going to override that on, and the result the light will be off. On and off is kind of the same thing, just a different order. And on, when both light switches are on, is the only way that the light in the room is coming on. So that's the results of an AND gate. And what a truth table is. A list of our inputs. An OR gate, again, it's a binary operation. That piece of chalk got too small. A or B, and then an output. So kind of the same thing. There's 2 inputs, so 2 to the 2 squared, there's going to be 4 outputs. So 2 offs, 2 ons. Cut that in half. Off, 1 on, 1 off, 1 on. And OR is either one. If anything's on, it's going to trigger that. So like what I just said with the light switch, both of them have the rooms where both light switches have to be on. This is more like a 3-way light switch. You'll often find those by staircases in American homes, where there's a light switch at the bottom of the stairs and a light switch at the top of the stairs, and they kind of alternate. If either one of them is turned on, then our light comes on. But if they're both turned off, that's the only way the light goes off. Then if either switch is on, off or on, well, with OR, there's an on there. So our result's going to be on. And same thing here. On or off, well, we had an on. True and false might make more sense here. False or false is obviously false. But false or true, it's like, we're going to grasp for any truth we can find. There's some truth there, so we're going to hold to that truth. Or using the value of true and false with an and, and is the truth, the whole truth, and nothing but the truth. So only when everything is true, only when all the inputs are true, will the output be true. And or is just any little thread of truth we can find. If there's any truth in there, our output will be true. So again, there's different ways we can phrase it to make sense out of it, depending on the situation. Then we had those others we looked at. So NAND, or not and, A, B, and output I'll draw this one quickly. It should make sense because it's the opposite of this. I'm down to just little bitty pieces of chalk. I guess I need to get one out. 0, 1, 1. And 0, 0 and 0 would be 0, but we want to negate that. So the negation of that would be on. And everything here, if it was and, that would be off, but when we negate it, we'll get on. Same thing on the next row, just the other order. Then normal, on and on, true and true, the truth, the whole truth, nothing but the truth. With and, that's how we get true out of it. But then when we negate it, that's the only way we get false out of it. Similar thing with NOR. It's the output's the negation of OR. So A, B, and out. 0, 0, 1, 1, 0, 1, 0, 1. And so if they're both false, false or false would be false because there's only false, but then when we negate that, we get a true, and everything else, when we negate it, we'll get a false. So that's the truth tables of our basic ones. Oh, I guess I'll got a little room up here. I can write the XOR. Exclusive OR. So it's just like OR, one or the other, but not both. So exclusively, one's off and one's on. Yeah. One's true and one's false. So 0, 0, 1, 1, 0, 1, 0, 1. So off, XOR off is going to be off. And exclusive off. Exclusive OR, so off, exclusive OR on, they're different. So the output will be on, or true. True, XOR false, they're different, so the output's true. But true, XOR true, since they're the same, the output would be off. And that's kind of what our main gates look like. So one more thing to talk about, and then I'll build a slightly larger truth table for an example of that. But I keep mentioning true and false. Where do these true and false come from? So that's the next thing. I'm going to erase the board, and let's see where we get our true and false from. One more set of operations. So where do these true and false things come from? One more set of operations, and you already know these. The comparison operators. So what sort of comparisons do we have? Right off the bat, one we've already mentioned, equality. Right? And in math class, if we're writing equals, equal to, or equality, we try an equal sign. Excuse me. But we want to be careful because in most languages, we use the equal sign for assignment. When we set up a variable, we're going to do some stuff, and one equal sign means we use that for store whatever that is in a variable. So that's an assignment. So for equal to, we use two equal signs. And I always say it like that. Equality, I always state as equal to because it helps me remember two equal signs for equal to. Then, well, we have equal to, or it could be not equal, which we have a symbol for not, and just not equal. Then obviously we have smaller or bigger. So smaller or bigger, less than, greater than is the way we would say that in math class. But when we're trying to think through a situation and figure out the solution to a problem, less and more might make smaller or bigger, less and more. Those words might make a little more sense. But we also have that with equality. So we can also have less than or equal to is how we would say that in math class. The English way of phrasing it would be at most. So the biggest it's going to be is whatever's there. Or the other one, greater than or equal to what we would say in math class, and we don't have that symbol like we write in math class with a line under it. So we just go write two symbols. So less than or equal to, because we have both symbols on the keyboard. And the typical way to say that would be at least. So in math class, we say greater or equal, and in normal English, we would say at least some number. So that is where we get our truth values. So x equals 3, y equals 5. And we can do these comparisons. So x equal to y would be false, right? And these are our true false. We make the comparisons to get our true false in boolean algebra, and then we use the logical operators to combine those true false to build up more intricate things. X not equal to y. It's true, right? I didn't state it, so hopefully you realize that pause there. I was hoping you're going to answer while you're watching the video. Well, under that, y smaller than x should be false, right? Y bigger than x. Yep, 5 is bigger than 3. So that one's going to be true. What else is there? Yeah, then we could add the equality. X less than or equal to y. Yeah, 3 is smaller or equal to 5. So that one would be true. So it's the comparisons like you're probably familiar with from math class. That gives us our yeses and nos. Yes, no thing. And then we can combine those up. So let's make a slightly larger truth table for an example of something other than those trivial, just what the gates show. So I'm just going to make this up here. I'll keep these around and add in some more. Z equals 4. That looks like it goes right there nicely with those. So let's say not x less than y and x not equal to y or z greater than y. So we can use our logical operators to build up combinations like this. And then we have our order of operations. I dropped a piece of chalk. Sorry. I dropped a piece of chalk and it always feels weird when I'm standing on step on them. So I was trying to see where it fell, but I have no idea. So we can build up combinations with our comparisons. And now we just have to follow the order of operations to get through this. And we could, we'll walk through it with order of operations and then we'll build a truth table out of it. We'll look at it both ways. So x, so we want to do parentheses first. Right? Do any groupings first, so the parentheses first. X less than y. Well, 3 is less than 5, so that's going to be true. Not true. And x not equal to y. Well, 3 is different than 5, so that one's true. Or z bigger than y. Or bigger than 5 is going to be false. So now we need to, our next one is the unitary operations, the not, because it only negates the first thing. So not true will be false. So we have false and true or false. So false and true, well, and is inclusive, so false and true is going to be false, because we go left to right again. So false or false. And false or false will be false. So our end result comes down to false. And then we could put this in a truth table as well. We could call like this statement A, this statement B, and this statement C. And then build up a truth table from that. A, B, C. And really we need not A. We don't need A. We don't need A. We need not A. So let's add that into a column. And then we could do the combinations. Not A, and B, and then whatever that is, I ran out of room. I'm going to call that Q, just because I ran out of room. Then Q or C. Just making up another letter to put in there. So our options for A is I left variables there because like, we might get different inputs from the user. So our options for A, well, really we have 3 inputs. So we should have 8 things. 0, 0, 0, 0, 1, 1, 1, 1. Probably could have left a little more room there. And our options for B, we'll cut that in half. Our options for C, 1, 0, 1, 0, 1. Then not A is just the negation of this. So whatever this, the not of this column and this. So A is 0, we want to negate that. We take the 1, 1 and 0 gives us a 0. 1 and 0 gives us a 0. 1 and 1, well that'll give us a 1. 1 and 1 gives us 1. And the rest of these are going to be zeros when we negate them, so 0 and we don't even have to check the other because we're looking for inclusion and we already hit a 0. We're looking for inclusion and we already hit false. So the rest of those are going to be zeros. So then this, whatever's in this column, which I guess I could try to write that out. Not A and B. So what's in this column or what's in this column? So 0 or 0 is a 0. 1 or 0 is a 1 because it's an or. 0 or 1 is a 1. 1 or 1 is a 1. 0 or 0, 1 or 0, 0 or 0, 1 or 0. So that's what a truth table will look like in a more complicated situation. So we have all the possible combinations of inputs, all our inputs, then the combinations of those inputs split up into 2 columns there to try to keep it a little straight. But this is probably what you're going to do most of the time. You can go through with the order of operations, like you know from math, and just do what's in the parentheses, do all the parentheses, then do all the negations, and then go through and do all the ands and ors. But somehow we're going to think it through, because now we are ready to apply this. So now we're going to take all this stuff we just talked about, and this is where I'm going to split up the label. So this is going to end lecture 1 for the week, and the next part is going to be lecture 2, which is going to be applying this and building selection structures, our selection construct. How do we make selections in our code? So that's the next video coming up very shortly.